friends, my name is Javed Akhtar and today we are going to learn binary search tree. But before learning binary search tree, let us recapitulate till now whatever we have discussed. So till now I think 12 lecture has been completed, and in this 12 lecture, previous 12 lectures, whatever we have learned are these. First we have learned that what is tree, then application of tree, then basic terminology of tree, that is height, depth, like these things, what is node, what is leaf node, and lots of stuffs we have discussed in case of basic terminology of tree. Then we have discussed what is types of tree. Now basically there are two types. In general, tree has two types. One is two-way tree, another is M-way tree. Okay, M-way tree is known as multi-way tree. Now in case of binary tree, whatever we have discussed is your types of binary tree, that is strictly binary tree, complete binary tree, and nearly complete binary tree. And then we have discussed properties of complete binary tree and properties of binary tree. Now after that we have discussed different kinds of binary tree. Just not we have discussed, but just we have taken the names of the different kinds of binary tree. That is binary search tree, APJ tree, and expression tree. Fine. Now under M-way tree, whatever the names, that kinds of M-way tree we have discussed. That what is the M-way tree first we have discussed, that fine. What is M-way search tree, then that is also defined, we have defined it. Now after that we found that there are two types of binary tree, and those M-way tree, B tree and B plus tree. So up to this we have discussed, but different kinds of binary M-way tree, that is B tree, B plus tree, we have not discussed. Now in case of binary tree we have discussed all, but we have just taken the names of the different kinds of binary tree, and the names are binary search tree, APJ tree, expression tree, heap tree, Huffman tree. These all are kinds of binary tree. This among that kinds of binary tree, now today we will discuss first one, that is binary search tree, that is BST, and the rest of the terms, types, kinds of the tree we will discuss after binary search tree. Okay, so let us today discuss what is binary search tree. Binary search tree is very important in tree data structure. Okay, so let us start defining it first. So what will be the definition of binary search tree? Okay, let us discuss the definition of binary search tree. A binary search tree is a binary tree that is either empty or in which each node contains a value, that is key, that satisfies the following conditions. And the conditions are: all keys in the left subtree of the root are less than key in the root. All keys in the right subtree of the root are greater than the key in the root. And the left and right subtrees of the root are again BST, that is binary search tree. So suppose we are creating here a tree. If it is empty, there is nothing, so of course there will be a root which is having null value. So that first, a binary search tree is a binary tree that is either empty, so it's a binary search tree which is empty. Okay, that's simple. And in which each node contains a value key. If it is not the empty one, then each node will contain a value. So suppose there is a value 30. Okay, that satisfies the following condition. So suppose we are creating some tree, this is 20, this is 40. Of course it is binary, that's why only two children is possible. Suppose this one is 10. Fine. Okay, so all keys in the left, so these are nodes which is having some value, that's why there is citizen and contains some value. If it is not empty, then the nodes of the tree will contain value. That's the binary search tree part of the definition first. So to be a binary tree, a binary search tree, you need nodes which is having some value first. Okay, then what you need, all keys in the left subtree of the root are less than in the right less than the root. So this is root, as you can see, and left of this root is 20, which value must be less than the value of the root, which is true here. 20 is less than 30. Fine. And all keys in the right subtree of the root are greater than the key in the root. So right of this root is 40, which is greater than root node. That's also satisfying. Now the left and right subtree of the root are again binary search tree. Okay. So this one is the total left subtree of this tree with node root node this 30, and this one is the right subtree of this tree with root node 30. Okay. So again it is saying repeatedly that this subtree must also be binary search tree. So again this subtree must also satisfy the whole definition again, and the definition says if it is not empty, then left all keys in the left subtree, then it must contain some value. So these are subtrees with nodes containing some value. That's binary search tree. And the left of the root. So in this subtree, root node is 20. Fine. Left of this must be less than the value than the root node. That's also fine. And right subtree of it is empty. So a root node, a right subtree is again a tree. That can be empty. See, there is empty. So this is right subtree which is empty. And right subtree is a BST which can be empty as it is shown. Now in the left subtree, this one is only. So 10 is a left subtree with one value, and left of this and right of this empty. So that can also be possible because BST says that either it is empty or it is having some value with following condition. So this is the definition. So in recursive way we can define binary search tree that there is a node, okay, and it is a tree is, if it is empty then also it is binary search tree. If it is not empty, then it must contains nodes of the tree, nodes of the binary tree, mind it, because BST is the kind of binary tree. Okay, so the nodes of the binary tree must be containing some value, and after that what it makes the binary tree, that binary search tree, it is the following condition. The following condition says that if the left part of the tree, that is subtree, contains values lesser than, all values lesser than the root, and right of the part contains all value greater than the root node. Fine. And repeatedly the left subtree and right subtree must also satisfy the whole definition of the binary search tree. Then it can be you can say, or we can say that binary tree is binary search tree. Fine. Now one more thing here, that we should note that there must be no duplicate node. Why? Because whenever we insert a node, any node, we compare the 30 whether it should be less than or greater than. Suppose already 20 is there, now again you want to insert 20. How you will insert? Here it is 30, that's fine. So 20 is less than 30, that should go here, but already 20 is present. Where you will place 20? Here. If you place 20 here, then left of that 20 must be lesser than that, but it is not the case. So it is, you cannot put here 20. If you put here, you cannot put 20 here, because that must be greater than 20. And again here you cannot put 20. So what we can say, that duplicate nodes, nodes with duplicate value are not allowed in binary search tree. Now let us construct a binary search tree using some value, and we using with this following this we will follow this procedure to construct that binary search tree with given some value. So let's do that. Okay. Is saying that draw a binary search tree with following sequence. So this sequence is given, and you need to we need to draw a binary search tree. So let us know how it can be drawn. So by following by following the definition of binary search tree, we can construct, and here we can in this draw in this way. So first node is value 50. So it's a 50 value with a node. Fine. Now another value is 30. We need to insert that 30. Where we will insert? In left or right? Because 30 is less than 50, so we should go, of course, by following the binary search tree property, that left part will be the lesser than the root node. So it will be lesser than this 30. Now 10 is lesser or greater. 10, every time whenever we need to insert any value, we will first start from the root node, not from here, not from here, not from anywhere else. We will first check the root node. So 30 done. 10 we will start from here. 10 is less than 50. Fine, less than 50. We will go here. 10 is less than 30. Yes, 10 is less than 30. So we will construct this here. Now 90 is greater than 50. So we will go here and we will construct here. Now 100 is greater than 50. So we will go right side of the 50. but 100 is again greater than 90, so we will go for here. So that's it, 100. Fine. Now 40 is less than 50, we will go here, but 40 is greater than 30, so we will construct it here because 40 is greater than 30. Now 60 is less than or greater than 50, so we will go in right subtree of 50, so we are coming here in this. Now in right subtree, which one is the root node? 90. So compare this 60 with this 90. Less or 60, less than or greater than? 60 is greater than or less than? 60 is less than 90, so we will draw it to the left because this is root node for the 60. If for this binary search tree, that is a subtree, and that value is less than 90, that's why it is here. Now 20 is less than 50, we will go here. Fine. 20 is less than 30, we will go here. Now 20 is less than or greater than 10. 20 is greater than 10, so we will construct in right of the 10. Fine. Now 5 is less than or greater than 50. 5 is less than 50, we will go here. 5 is less than 30, we will go here. 5 is less than 10, so we will go here. So in this way we can construct a binary search tree with any given sequence. So this is a binary search tree. Fine. Okay, now there is one very important property of binary search tree, that whenever you traverse, we have covered the traversal part of any binary tree. So binary search tree is also a binary tree, of course. So when we traverse this binary search tree in order manner, then what we get, that the output will be that the way in which we will be visiting, if we mark the points that which one is visited, which node is visited first in the sequence, then we will write it, then we will find it that the sequence obtained after the traversal of this binary search tree in order manner, we find that the sequence obtained is in increasing order. Okay, so in that case we will get that in increasing order, of course. So it is sorted, of course. So a binary search tree can also be when it is, if you have some data like this, you construct a binary search tree with this data, and what you will get, if you traverse that binary search tree in order manner, you will get this data in sorted order. So it's kinds of a sorted part. By using this property, we can also sort a sequence of numbers. Okay, so let's traverse this tree to understand in order manner to get the sorted value of this sequence. Okay, so traversal part, in case of in order manner, if you want to traverse a binary search tree in order manner, then what the algorithm we had followed earlier, I'm not going to discuss that again. You can go to that lecture and see how it has been shown there. Now we will just traverse it, and the algorithm was in such a way that abbreviated as first you traverse left, then visit the node, and then go for the right subtree. So first you complete the left, then visit, and then go for the right. Okay, so in this way we will traverse. Another part, during this discussion of the traversal, in case of any traverse in order or pre-order or post-order, we have used a stack, because whenever we write some program in recursive manner, we use a program uses that in that stack whenever we call the function. Okay, so that we will again use for traversing part. Okay, to traverse in order a binary tree, of course we can say binary search tree, then we need to start from the root node. So let's start. We'll start from root node, that is 50. So 50 in order, 50 has been called. Now check it is null or not. If it is not null, then enter inside and call in order again. What? With left of that part, that is left of this left subtree. Left subtree of 50 is this one with root node 30. We call the in order function with this tree, and root of this tree is 30. So we will call it again. So in order has been called with value 30 again. Again it will be called. So in order we now here we are with value 30. Then we insert it, we go here, then again we will check it is null or not. It is not null. Go for the left. See, in order with left. So go for the left subtree with value 10. So we will call it again in order value with value 10. In order procedure with value 10. Now go not null. Okay, left of the okay, fine. 10 is not null. Fine. In order we will call it with left. Left is 5. So again 5 in order with value 5 will be called. Now again go check it is null or not. 5 is not null. Come inside. In order left will be called. But left will be called, but left is value null. So suppose this value in order has been called with what? Null, because left of 5 is null. So it will go here, it will try to enter, but as root of this left subtree of the 5 is null, so it will not be allowed to enter in this algorithm and it will stop here. After stopping, where we are now, we are at node 5. See, it has not been called. Fine. So we are removing it. Now we are presently at root node 5. Fine. So what we are doing here, after that we will visit. That means 10. Sorry, 5. We are present at 5. So we need to visit here because presently we are here. So we are visiting 5. So we have visited 5. So first node which is visited is 5. In this way, again we will call again in order with right. Okay. So I am not going to discuss it again. Discuss the whole explanation part because already I have discussed in lecture in which we have discussed in order traversal. So I am just going to write the sequence in which it will be nodes will be visited. It will be the sequence in which it will be nodes will be visited. So we will visit first 5, then 10, then 20, then 30, then 40, then in this order, in this sequence we will visit. If we traverse a binary search tree in order manner, then what we get? We get nodes visited in a sequence, and that sequence is in increasing order, and that is this. So it is a sorted one. So it's sorted. Fine. This is the property of binary search tree. Okay, let us do another problem with regarding construction of binary search tree with some given string. Earlier it was value, now it is string. But string does not have value as we know. But how we will construct a binary search tree? Because to construct a binary tree we need to compare with value. Okay, but in here as we can see that it's a string. How we will make it realized with value so that we can construct a binary search tree with this sequence? So the idea is that first we will compare the first letter of that. So suppose I am constructing a tree and I will start from here and I will start here MAR, and then I need to insert May. So I will compare the first letter. Okay, so M comes after M, no, M comes before M, no, so it's not working. So we will go for the next letter. Next letter we will compare, that is A and A. Again A and A. Whether A is less than A? No. A greater than A? No. So we will go for again R. So whether R is greater than Y? No. R is less than Y? Yes. So why? Because Y comes after R. Okay, so we will understand in this way that as Y comes after R, so Y is greater than R. Okay, so it's our conceptual understanding. In that way we can say that May will come, as Y is greater than R, so May will come in right of Mars, that is May. But that's the conceptual part we will draw in manual way. Okay, now what we will do if we want to write a program for that. So I cannot say to computer that as Y comes after R in this way, but that can be told to the computer but in different fashion. So here we will use a ASCII value. Okay, so ASCII value, as we know that capital, I am talking about capital A to Z is starting from 65. So 65A, B is 66. So see, each letter is resembles a value, that is ASCII value. 65, 60, B is 65, C is 67. In this way we follow. So each letter can be seen in a numerical value. Okay, So in that way, now we can write program, because programmatically now we can compare. So in program, what we do, we compare ASCII value actually. So when we say r is less than y, what we mean that ASCII value is of r is less than ASCII value of y. That's the programming part. Okay, so when we will do program, we will do in that fashion using that ASCII value concept. So now let us, we don't need manually first construct it. Okay, so first one is March, MAR. So it's a root first. Second comes May. As we have discussed it, it will be coming in right, MAY. Fine. Now comes November. See the first letter NNM. Which one is N? LMN. M is less than N. So N is greater than M. Fine. N is greater than, fine. So M is N is greater than M. Fine. So we will go right. Now we will compare here. Again, November will be compared with MAY. See, again N is greater than M. See, N is greater than M. So it will come here and we will write November here. Fine. Now we will write August. August, see, A. First letter compared. A is less than M. So it will go here. August. Now April. A is less than M. Fine, it will come here. AA. Both are equal, we cannot compare. P and U. See, U comes after P. So P is less than U. So we can say that it will go left as P is less than U. So April, APR. Now January. J is JKLMN. So J is less than M, of course. J is less than M. So it will go left. Now J is greater than A. So it will go right and it will be written here, January. Then December. D is greater than M. No, D is less than M, so it will go left. D is greater than A, of course, so it will go right. But D is less than J, so it will go left. So DEC. Now July. JUL. J HIJKL M. So J is less than M, so it will go here. J is greater than A, it will go here. J is equal to J. Here J is equal to J. First letter equal. So we cannot compare. So A and U will be compared. A is less than U. U is greater than A. U is greater than A. So it will go right. So JUL. Fine. February. FEB is less. F is less than M. Come here. F is greater than A. Go right. F is less than J. Go left. F is greater than D. So go right. So FEB. Now June. J is less than M, go left. J is greater than A, go right. J is equal to J, fine. We will compare U, NA. U is greater than A, go here. Now J, U, both are same. We cannot compare. So we will compare the third letter, that is N and L. N, K, L, M, N. L comes earlier. So N is greater than L. So it will go right. So JUN. Now OCT. O is less than M. LMNO. M and O. O is greater than M. So go right. O is greater than M. Go right. LMNO. O is greater than N. So go right. So right here OCT. Fine. Then last comes September. MNOPQRS. S is greater than M. Come here. S is greater than M. Come here. S is greater than N. NOPQRS. N is greater than, yes. S is greater than N. Fine, go here. OPQRS. S is greater than O. So go right here. Right is September. So in this fashion, we have constructed the binary search tree if a string value is given to insert in a binary search tree. So that's fine. Now, as we have constructed this, now let us understand what is this operation. What is the operation we do on binary search tree, like insertion, search, and deletion. Okay, traversing we have seen. How we will insert. How we will write an algorithm for insertion part. So before, as we know that as a student, what we should always ask to ourselves before doing anything, solving any problem, writing anything, is what and why. So before writing the algorithm insertion, we need to understand how we will write before writing the algorithm, because we must know, because we cannot write the algorithm and we can write it. We need to first know that how we can do it manually, and then we can go convert that concept to write the algorithm for that. So let us understand first the first operation. So understand first the insertion algorithm, and before that we will understand how to insert any node in a binary search tree.